Welcome to the deep dive.
Mm.
Our goal here is pretty straightforward. Take all these complex sources you shared, sometimes really dense stuff, and basically give you the shortcut to really getting it. Today, wow, we're going deep. The materials you sent, they're all about the most exotic ideas in physics, black holes, wormholes, time itself. We're going to try and make sense of it all. Show you this isn't just sci-fi, it's real complex science.
Absolutely. And, we can only really tackle this because of two huge breakthroughs from the 20th century, general relativity and quantum mechanics. I mean, these ideas, they're behind almost everything modern, computers, GPS.
Right, even your digital watch relies on this stuff.
Exactly. And also the framework for understanding, well, stars collapsing and maybe even time travel.
And that's the thing, isn't it? The sources jump right in by challenging how we normally think about time. We all kind of feel like time just flows, steady, 1 second per second for everyone, everywhere, like a constant background noise.
Yeah, but that background, it's not real. Not universally, anyway. That's maybe the first big shocker here. Modern physics tells us there's no single cosmic clock ticking away for the whole universe.
No absolute time.
None. And get this. We know, really know from experiments, that time travel to the future, it's possible. It's been tested, proven. The science is called special relativity. That's our starting point.
Okay, time travel to the future is proven. That's huge.
Yeah.
But to really get why time behaves like that, we need to talk geometry first, because time and space are linked. Space-time. Let's do space first.
Sounds good.
We live in 3 dimensions, right? Forward, back, left, right, up, down. But trying to imagine a fourth spatial dimension, like another direction perpendicular to all those, our brains just can't.
Nope, it's a real mental hurdle. That's why thought experiments are, well, essential tools here. To understand how our 3D space might curve, something we can't directly see, we can imagine dropping a dimension.
Like flatland.
Exactly like flatland, or a 2D world. Imagine beings living on a perfectly flat surface. They only know forward, back, left, right, a third dimension, up or down. Totally inconceivable to them.
But we can see their world from our 3D view. We could, say, lift something out of a closed box they've drawn, right? We just move it up.
Precisely. We reach down into their world, pick up an object from inside a circle they drew, and put it outside. To them, it vanishes from the inside and just poof, appears outside. They have zero concept of the path it took through the third dimension.
Okay, so it's a neat trick, but what's the physics point?
The point is curvature. That 2D analogy helps us think about how our own 3D space could be curved. Imagine those 2Ders weren't on a flat plane, but on the surface of a huge sphere.
They could figure it out, couldn't they? Without leaving their 2D surface.
They could. If they drew a really big triangle, the angles inside wouldn't add up to 180 degrees, it'd be more. That tells them their space isn't flat, it's curved. We can actually do similar measurements in our universe, though on a local scale, it looks incredibly flat.
Which brings us to gravity. Because gravity is what does the curving, right? Newton thought of it as some kind of invisible rope.
Yeah, an instantaneous pull between things with mass. Very mysterious. But Einstein, he just threw that whole idea out with general relativity.
So what was Einstein's idea?
For Einstein, gravity isn't a force pulling things. It is the curvature of space-time itself. Mass and energy actually warp the geometry around them.
Like the classic bowling ball on a rubber sheet analogy.
That's basically it, yeah. A heavy object like the sun creates a big dent in space-time. The Earth isn't being pulled by the sun.
It's just rolling along the curve.
Exactly. It's following the straightest possible path it can through that warped geometry. That path is called a geodesic. Think about flying from London to New York. The shortest path on a globe looks curved on a flat map, right?
A great circle route.
Spot on. A geodesic is just that concept, but for paths through four-dimensional space-time.
Okay, to really nail this Einstein idea, we need the equivalence principle. The sources really hammer this. Feeling acceleration, like being pushed back in your seat when a car speeds up. That feeling is identical to feeling the force of gravity.
Completely indistinguishable. It's a brilliant thought experiment. Imagine you're in a sealed room, like a windowless rocket. You feel your feet pressed to the floor. Are you sitting on a launch pad on Earth, feeling Earth's gravity? Or are you way out in deep space, accelerating upwards at precisely 9.8 meters per second squared 1g? There's literally no experiment you could do inside that room to tell the difference. Acceleration feels exactly like gravity.
Which connects to that weird feeling of free fall, right? Like astronauts orbiting Earth, they feel weightless, zero gravity. But gravity's still there, holding them in orbit.
It is. What's happening is their constant acceleration towards Earth perfectly cancels out the sensation of gravity. They're falling, but also moving sideways so fast they keep missing the planet.
So if you drop something while you're in free fall,
It just floats right next to you because you're both accelerating downwards at the same rate. And this leads to a crucial insight for Einstein.
okay,
If acceleration is equivalent to gravity, and we can imagine that accelerating upwards in that rocket would make a horizontal beam of light appear to bend downwards inside the rocket.
so if acceleration bends light and acceleration is the same as gravity,
And gravity must bend light too, which is exactly what observations confirmed during a solar eclipse in 1919. Starlight bending around the sun, massive proof for general relativity, mass warp spacetime, and light follows that warped path.
and the most extreme warping imaginable is a black hole.
The ultimate gravitational monster, yeah. We know they're out there. They form when a really massive star runs out of fuel, explodes in a supernova, and its leftover core collapses under its own gravity. If that core is more than about 3 times the mass of our sun, nothing can stop the collapse.
They sound terrifyingly complex, but the sources say they're actually simple.
Structurally, yes, at least in theory. A black hole is defined by just 3 things. Its mass, how fast it's spinning, and its electric charge. That's it. But what those properties create is extreme.
You have the singularity.
Right at the heart, a point where all that mass is crushed down to, well, theoretically infinite density. Our current physics breaks down there. We just don't know what happened.
And then the boundary around it.
The event horizon,
Yeah.
also called the Schwarzschild radius, that's the crucial part. It's the point of no return. Because inside the event horizon, the escape velocity, the speed you need to get away, is greater than the speed of light. Since nothing can go faster than light, nothing escapes. Not even light itself.
But outside the horizon, gravity is just strong, not inescapable.
Exactly. Strong but finite. You could orbit a black hole safely, just like orbiting a star, provided you stay outside the event horizon. They don't, vacuum up everything in the universe. Their intense gravity is a local effect.
Okay, let's swing back to time. We've talked about space curving. Time is the other part of space-time. Special relativity, the thing that proves future time travel, is based on 2 ideas, the sources say. And the second one is the really weird one.
The speed of light.
It's constant.
Yeah.
Always. Doesn't matter how fast the light source is moving towards you or away from you, doesn't matter how fast you're moving. You always measure light speed as the same value, the ultimate cosmic speed limit.
And that's the core problem Einstein wrestled with. If everyone, no matter how they're moving, measures the same speed for light, then something else has to give.
Space and time can't be fixed.
They can't be absolute and rigid like Newton thought. They have to be flexible, elastic. They must stretch and shrink depending on your motion, precisely so that the speed of light stays constant for everyone.
And that stretching and shrinking is time dilation, the future time travel thing.
That's it, time dilation. Think about a clock made of light bouncing between 2 mirrors. If that clock is sitting still, the light goes straight up and down. Tick-tock. Now, imagine that same clock zooms past you at, say, 90% the speed of light. From your perspective, watching it go by, the light inside isn't going straight up and down anymore. It has to travel a longer diagonal path to hit the mirrors.
Right, because the clock itself is moving sideways.
Exactly. But, and here's the key, the speed of light is constant. So if the light has to travel a longer path, but its speed doesn't change, it must take
Longer. It takes longer for the light to complete one bounce.
Precisely. So you, the observer, watching the fast clock go by, conclude that time inside that moving clock is running slower than your own time. Time itself has dilated, stretched out for the moving clock.
And this isn't just a thought experiment. This happens.
Oh, absolutely. Constantly verified. Particle accelerators like CERN smash particles together at incredible speeds. Short-lived particles like muons, when accelerated close to light speed, their lifespan dramatically increases compared to identical muons just sitting still.
They age slower.
They literally age slower. They travel into their own future relative to us in the lab.
Which is the famous twins paradox, essentially. One twin, Alice, zooms off in a spaceship near light speed, comes back, and she's physically younger than her stay-at-home twin brother, Bob.
That's the one. And the paradox isn't really a paradox because the situation isn't symmetrical. Alice is the one who had to accelerate, turn around, decelerate. That acceleration breaks the symmetry and makes her the younger one upon return. It's real.
Okay, this elasticity of time leads to something even stranger, right? The block universe.
This comes from something called the relativity of simultaneity. Because speed affects time, Observers moving relative to each other won't agree on whether two events happening in different places occur at the same time. There's no universal now.
No universal present moment across the cosmos.
Correct. And if there's no universal now, then the distinction we make between past, present, and future starts to look, well, subjective. An illusion created by our motion through spacetime.
So, for many physicists, this implies
It implies the block universe model. If spacetime is this unified four-dimensional thing and now is relative, then maybe the past, present, and future are all equally real, all just existing, like different locations on a map, but the map includes time.
like a movie reel where all the frames exist simultaneously, even though we only experience one frame at a time.
That's a decent analogy. Every event that ever was or ever will be is just there,
That-o.
fixed within this 4D block of spacetime. It's a really profound and honestly kind of disturbing idea. It really challenges our notions of free will.
All right, so future time travel, proven,
Mm-hmm.
happens all the time with fast particles. But the big one, the sci-fi dream, traveling to the past, that seems way harder.
Oh, vastly harder. Theoretically, anyway. To go backwards, you need more than just slowing time down. You need to warp space-time so much that you create a pathway that loops back on itself. A closed, time-like curve.
A loop in time.
Essentially, yes. And the theoretical gadget for doing that is a wormhole.
Okay, wormholes, shortcuts through space, or maybe time.
Potentially both. Think of them as tunnels connecting two different points in space-time. Maybe 2 points very far apart in space, or maybe 2 points separated in time. But there's a huge catch to making one you could actually travel through.
They need something weird.
They need something really weird. To keep the throat of the wormhole open, to stop it from collapsing instantly due to its own intense gravity, you'd need what physicists call exotic matter.
Exotic matter. Sounds like it powers the Starship Enterprise.
Huh. Well, it's matter that has negative energy density, or negative pressure. Basically, instead of pulling things together like normal gravity, it pushes space-time apart. It props the wormhole open.
Does that even exist?
Amazingly, yes, kind of. We can create tiny, fleeting amounts of negative energy in the lab using something called the Casimir effect. Put two metal plates very close together in a vacuum, and the quantum fluctuations create a slight negative pressure between them.
But just tiny amounts. Not enough for a wormhole.
Nowhere near enough. We're talking microscopic effects. Building a stable, human-sized wormhole would require vast amounts of this stuff, and we have no idea how to make or handle that.
Okay, but if we had one, a stable, traversable wormhole, how does it become a time machine?
You use time dilation again. Imagine you have the two mouths of the wormhole, let's call them A and B, initially sitting next to each other, both existing in, say, Wednesday.
Right.
Now you take mouth A on a very fast trip, near light speed, maybe for a few hours of its own time, and then bring it back next to mouth B. Because of time dilation, less time will have passed for mouth A than for mouth B.
So mouth B is still on Wednesday, but mouth A is now further in the future.
Or rather, mouth B has aged more. So maybe mouth B is now on Thursday, while mouth A is still effectively on Wednesday afternoon. Now step into mouth B on Thursday.
And you come out of mouth A on Wednesday. You've traveled back in time.
That's the theoretical mechanism. But as soon as you propose this, you run headlong into paradoxes. Big ones.
Yeah, the obvious question. If this is possible, where are all the time tourists from the future?
Exactly. The biggest theoretical headaches are the inconsistency paradoxes. The classic is the grandfather paradox. You go back, accidentally prevent your grandparents from meeting, so you are never born. But if you were never born, you couldn't go back to, well, you see the problem, it's a logical contradiction.
Total meltdown. But the sources mentioned another one, maybe even weirder, the something from nothing.
Ah, yes, the information paradox or bootstrap paradox. Imagine finding a complete diagram for building a time machine inside the time machine you just built. You use the diagram, build it, succeed, then years later, you put the same diagram back into the machine for your younger self to find.
So where did the information, the diagram, originally come from?
Nobody knows. It just exists in a self-contained loop created by no one. Or think of Shakespeare finding a copy of Hamlet in a time machine, copying it out, becoming famous, and then putting the book back in the machine for his younger self. Who actually wrote Hamlet?
Okay, my head hurts now. How do physicists try to solve these paradoxes?
Oh, the most popular, maybe most elegant solution comes from quantum mechanics, the many worlds interpretation, or the multiverse.
Parallel universes.
Basically, yes. People like David Deutsch argue that when you travel back in time, you don't actually arrive in your own past. You cross over into a parallel universe, one that's identical up to the point you arrive.
So if I went back and stopped my grandparents' meeting,
You'd just prevent the birth of your alternate self in that universe. Your own history in your original universe remains completely unchanged. No paradox. You just create a new branching timeline. It neatly solves all the inconsistency and information paradoxes.
that is neat. But is there any reason to think nature wouldn't allow past time travel, even with many worlds?
There is. Stephen Hawking was famously skeptical. He proposed the chronology protection conjecture. His idea was that the laws of physics themselves conspire to prevent time travel into the past. He speculated that the very act of trying to form a closed time-like curve, like turning a wormhole into a time machine, would cause quantum effects, specifically virtual particles and vacuum fluctuations, to run wild. They'd build up to infinite energy density right at the entrance, essentially destroying the wormhole or making it unstable the instant it becomes capable of time travel.
So nature slams the door shut.
That was Hawking's bet. The universe protects its own history, whether he's right or whether parallel universes offer a loophole. Honestly, the jury is still very much out. We're deep in theoretical territory here.
So as we wrap this up, it's worth remembering we've touched on the two great pillars of modern physics: relativity, ruling the large scale; gravity, the cosmos; and quantum mechanics, ruling the tiny scale, atoms, particles. And the big problem, they don't play nice together.
They're incompatible, mathematically.
Deeply incompatible in their current forms. Finding a single framework that unites them, a theory of everything, that's the holy grail. Theories like M theory or string theory try to do this, often by proposing, well, more dimensions, like maybe 11 dimensions in total. 11 dimensions. It really is mind-boggling to think that things like black holes, time warps, maybe even parallel universes aren't just crazy fiction anymore. There's serious possibilities arising from our best understanding of reality based on actual data.
They really are. And let me leave you with one final thought, something profound about time and the universe, something you can see for yourself. It's called Olber's paradox, and it's maybe the simplest, most visual proof that the Big Bang happened, that the universe isn't infinitely old.
Which is?
Why is the night sky dark?
Because the sun went down.
Huh. Well, yes, but think bigger. If the universe was infinite in size, infinitely old, and filled roughly uniformly with stars, then no matter where you looked in the night sky, your line of sight should eventually end on the surface of a star.
Like standing in a huge, dense forest, you see trees everywhere you look.
Exactly. The entire night sky should be blazing bright as the surface of an average star, maybe even as bright as the sun's surface. It should be blinding.
But it's not. It's mostly dark.
It's mostly dark. And that darkness tells us the universe is not infinitely old and static. It tells us the light from the most distant stars hasn't had enough time to reach us yet since the universe began about, well, roughly 15 billion years ago in the Big Bang.
Wow. So the darkness itself is evidence of the beginning of time.
It's the echo of creation written across the night sky. Something to ponder next time you look up.
That's a perfect place to end. Thank you for taking this incredibly deep dive with us today. Hopefully these ideas give you plenty to think about as you move through your own path in speed time.